This is a lecture about gases and in particular about the gas laws. Gases are really important in our life. They are what is responsible for pretty much all of our weather, the temperature, wind, humidity, and rain. This is just kind of a sideline of interest. Lots of people think the atmosphere is made up mostly of oxygen because we need that to live. But it's the vast majority of it is nitrogen. Oxygen is a good slice of it, though. All right, so some of the basic characteristics of gases that you've probably learned about for years, but it's kind of worth reviewing. A gas will expand to fill whatever container it's in. That's unlike liquid and solids, which have set volumes. Gases are highly compressible. You can squeeze them into smaller and smaller spaces. And that's simply because there is a large amount of space in between gas molecules. Gases form solutions with all other gases. Okay, remember that a solution is simply a homogeneous mixture. So regardless of the type of the gas or the chemical makeup of a gas, they always form solutions with one another. They mix totally homogeneously. Let's see. Oh yeah, this is unusual. We will go over this in a little bit more detail later in this lecture, but all types of gases occupy the same volume, okay? That's called Avogadro's Law, and we will go over it, as I said, a little bit later. All right, so one of the first theories that was proposed about gases, which under most circumstances still holds true, is the kinetic molecular theory. You'll often see it referred to in textbooks as KMT, and some scientists named Maxwell and Boltzmann proposed it, and it has 4 or 5 parts to it, but one of them is that all matter is made up of very small particles that are in constant motion. That is correct, and the kinetic molecular theory can be used to explain almost all properties of gases, and actually some of the properties of solids. So some of the key parts of the kinetic molecular theory are that the particles of a gas themselves take up negligible volume. In other words, the particles of gas are very, very small compared to the huge spaces in between the gas particles, okay? So in order to make calculations and understanding gases easier, the kinetic molecular theory tells us we can ignore the volume of the actual gas particle itself and only focus on the volume of the space in between them. The reason this is the case is because gas particles have almost no intermolecular attractions, okay? And because of that, they get far apart from one another, as opposed to liquids and solids, which have pretty hefty intermolecular attractions for each other. All right, another part of the kinetic molecular theory is that the actual kinetic energy of a particle varies directly or is proportional to the temperature. So that's kind of common sense, right? If we have a bunch of gas particles, and we increase temperature, they're going to start moving a whole lot more than they did at lower temperatures. So kinetic energy is directly proportional to temperature. I'll go into this a little bit later, but this theory and further exploration of it led to the concept of absolute zero. Alrighty. So you need to know, by the way, those 3 or 4 facets of the kinetic molecular theory. It a lot of times ends up being just like a multiple choice question on a test. One of the most important things to understand about gases are that they exert pressure and how to figure out what that pressure is. So it turns out that pressure from a gas results from molecular collisions of the gas particles against the container that it's in. So the bottom line is the more collisions there are against the container, the higher the pressure will be. So anything that increases the frequency of collisions of particles will increase the pressure. So what are the things that can affect the pressure of a gas? Well, clearly the number of gas particles in a container. If you have more gas particles, you're going to have more collisions, and therefore the pressure will go up. The volume of the container. If you put a bunch of gas particles in a small container versus, let's say, a much larger container, okay, you're going to have a lot higher pressure in the smaller container. There are going to be more collisions. Everything's going to be crammed in closer, and the pressure will go up. And the average speed of gas particles will obviously affect the pressure. The faster the particles are moving around inside the container, the higher the pressure. Okay? And obviously temperature is one thing that if you increase the temperature, you're clearly going to increase the speed and therefore the pressure. We'll talk about the effects of molar mass later because I don't think that's quite so intuitive. All right. So atmospheric pressure. We talked about pressure of gases. What do we mean when we talk about atmospheric pressure? Well, we all know that the atmosphere contains gas particles. Nitrogen, oxygen, carbon dioxide, all sorts of gases. Those gases actually have a mass to them. Okay? There is a weight associated with gas particles. And when you stack up all the gas particles from the surface of our Earth to way up in the atmosphere, that's a lot of gas particles that are pushing and colliding with us. That's what atmospheric pressure is, okay? It is the atmospheric gas particles colliding with us and putting pressure on us. So why don't we collapse under this pressure? We've gotten so accustomed to existing under atmospheric pressure that we don't even sense it. Let's talk a minute about living in a couple of different locations on our Earth. Let's talk about a location that's at sea level, and then let's talk about a location that is at the top of a mountain. Which of these locations experience higher atmospheric pressure? It turns out that the closer you are to sea level, the higher the pressure. So sea level positions experience higher pressure, higher atmospheric pressure, and way up on the top of a mountain experience lower pressure. Why is that? Well, if you look at this huge column of atmospheric gases pushing down on us, people that live on top of a mountain have less weight, literally fewer gas particles that are pushing down on them, so they experience less atmospheric pressure. Oops. How do we measure our atmospheric pressure? Well, originally we still use barometers, but originally the original or old-fashioned type of barometer had a pool of mercury. Hg is the symbol for mercury, and it's the only liquid metal we have. And scientists submerged an upside-down glass tube in a pool of mercury. And they saw the mercury rise up the glass tube to a certain distance. Well, scientists measured that distance that the mercury rose inside the tube, and they called that atmospheric pressure because they realized the gases from the atmosphere are applying pressure to the surface of the mercury in the open container, and that in turn is causing the mercury to climb up the tube, which is turned upside down in the container. And so it turns out that using mercury, the mercury would rise 760 millimeters up that tube, and so scientists began to call that atmospheric pressure. Well, pretty soon, scientists began using other units of pressure, one of them being atmosphere, another being torr, and we'll talk about all those later. But this is still the basic fundamental of how a barometer works. So as atmospheric pressure increases, let's say we have a real strong atmospheric front coming through, then the mercury will rise higher in the tube and the atmospheric pressure will be a little bit higher than 760 millimeters. All right, that's how we measure atmospheric pressure. We also have a tool that scientists use in the lab called a manometer, and that measures the pressure of some unknown gas. So let's say that scientists have collected some gas, they're not sure what it is, inside a closed container, and they want to know what pressure it's exerting, which will tell them a lot about what gas they have, how much of it is, etc. What they'll do is they'll hook it to a tube that is open to the atmosphere, and inside that tube they'll have a liquid, could be mercury or whatever, and that liquid will move around depending on the relative pressure from the atmosphere. And once the container of gas is open, that gas will also apply pressure to the other end of the liquid. And so depending on the difference in height between the liquid on the side of the gas and the liquid on the side of the open atmosphere, scientists will be able to tell what the pressure of that gas is. Okay, so it'll basically be the H, the difference in pressure between atmospheric pressure and the pressure in the gas. That is a manometer. Right, there's something called standard pressure, which is important to have memorized before we start all our gas laws. And scientists have just defined what are standard pressure conditions, because gases change phenomenally. Their properties do, depending on what the pressure is. And so standard pressure is 1 atmosphere, and 1 atmosphere is equal to 760 torr. 700 torr is actually equal to the unit millimeter of mercury. So anything you see in torr, you can also express the same exact number in millimeters of mercury. Of course, there is another commonly used unit called kilopascals, and 1 atmosphere is equal to 101.3 kilopascals. All right, so there were 4 properties that are used to define a gas, and they will show up throughout our gas laws. They're temperature, pressure, volume, and number of moles. Make sure you know the symbols that are used for them. The more common units, temperature, it's not a matter of being common. The only unit for temperature in gas laws is Kelvin, so you have to get used to that. And you might need to be reminded of the formula. So Kelvin, if you're solving for Kelvin temperature, it equals Celsius temperature plus 273. All right, so that'll be real important in this unit. Pressure, it's usually atmospheres, not always. Volume, usually liters, not always. This is an equivalency. You'll get familiar with this unit, 22.4 liters in 1 mole at standard temperature and pressure. What that tells you is that every gas, if it's at standard temperature and pressure, and we just learned standard pressure is 1 atmosphere, standard temperature is 0 degrees Celsius, which is the same thing as 273 Kelvin. So if a gas is under these standard conditions, it will occupy 22.4 liters volume. That is any gas, every gas, regardless of its identity. The symbol for moles is little n. So here we go with gas laws. We're going to start with what is called Boyles Law. Some memorization that you need to know here, so it'd be a good idea to jot a couple notes down, print out the PowerPoint, or make some note cards. Boyles Law looks like this, and it basically tells us that pressure and volume of a gas are inversely proportional. What does that mean? That means as pressure goes up, volume goes down. So I want you to think about holding a balloon in your hands. And as you squeeze the outside of that balloon, as you apply pressure, the volume of that balloon will go down. So that's what Boyles Law says. One of the everyday applications of Boyles Law is when we actually breathe. I think this is so cool. So you actually don't, breathing is involuntary, so you don't actually consciously or unconsciously tell your lungs to fill up and release air. What happens when your body decides you need to breathe is a little membrane called the diaphragm moves, and that causes your lungs to increase in volume. Look at Boyles Law. What happens when you increase in volume? They're inversely proportional. So when you increase your lungs in volume, pressure decreases. So you have this huge lung situation with the pressure has gone way down because you've increased your volume of your lungs. And what happens when pressure goes down? You create a little vacuum inside your lungs, and that little vacuum sucks air in to fill it up. And so breathing is really involuntary. Now, when your body feels that it has inhaled enough air, that little diaphragm will move back up, and that will cause the volume of your lungs now to go back down or decrease. Now that you have smaller lung volume, you have caused the pressure inside your lungs to increase, and that forces air to be expelled or exhaled. So let's move to an example. Oh, not an example yet. Okay, here's just a molecular interpretation of Boyles Law. It's kind of maybe easier to visualize for you. So if you have a closed container with a gas inside of it and a piston, and you push down on that piston, what have you done to the volume? You have made the volume go down. Therefore, what has happened to the pressure of the gas inside the container? Pressure has gone up. Do you remember what pressure is? Pressure is simply the frequency of collisions of the gas molecules against the container that it's in. If you make a smaller volume, you're going to have a lot more collisions and therefore higher pressure. All right, now if you were to graph, this is typically another multiple choice question you'll see. If you were to graph volume versus pressure, you'll see an inverse relationship, and anytime you plot an inverse relationship, you're going to see a downward curving line, and that's the case with Boyles Law. But in general, obviously, as pressure goes up, volume will go down. All right, this is just another cool example. Okay, so this might be, for example, an extra credit little essay question on your test. How is Boyles Law related to deep sea divers, scuba divers? Well, it turns out, I'm sure you know this, that as you dive down in the ocean, the pressure goes way up. Okay, so your body, lungs, every part of your body experiences higher pressure. Remember that atmospheric pressure is 1. And if you get down, let's say about 20 meters deep, your body is experiencing 3 atmospheres of pressure, which is a tremendous amount. And so what's going to happen to your poor lungs at that high pressure? The volume of your lungs is going to go down, and you're going to have a hard time breathing, aren't you? Obviously, divers have breathing apparatus to help with that. One of the biggest dangers for divers, though, is when they start to resurface. And if they do it too quickly, I want you to think of Boyles Law. As you go up, the pressure will be going down. Okay? Pressure goes down, down, down as you get closer to the surface. What's going to happen to your lungs as you surface and the pressure decreases? Your lungs will get larger. Okay? The volume goes up, okay? And that's actually dangerous because if you surface too quickly and the volume of your lungs expands too quickly, you can actually burst a lung, and that can be very, very dangerous. So divers have to, as you've probably heard, have to control their ascent very carefully. So I kind of explained all this to you already, but here it's kind of in writing if you want it, especially since I said it might be a multiple choice question. Okay, and again, I'll just give you a minute to read this. Okay, so the solution to that, and in addition to going very slowly from the depths of the ocean to the surface, is to always exhale when you are rising. If you're diving down, when you're coming up, exhale. Do not hold your breath. Right, so here's an example of a calculation using Boyles Law. Let's say you have 20.5 liters of nitrogen gas. You won't need it in this question, but just to remind you, nitrogen is one of the 7 diatomics, and they've given you the temperature and the pressure. And what have we changed here? We have changed the pressure, and it's now asking what's the new volume. So once you read through the entire question carefully, you can see that it is Boyles Law you will need, because Boyles Law allows you to predict a new pressure and volume from an original pressure and volume. Be careful with units. Okay, I'm trying to trick you here. I give you 2 different pressure units, and remember that units in gas laws for temperature always have to be Kelvin. If you'd like to try it yourself, give it a swing. If not, I'll show you how to work it on the next slide. Alright, Boyles Law. I'm first going to convert pressure units so that they're all the same. So 740 torr I want to convert to atmosphere, so I know the conversion factor between torr and atmosphere. There are 760 torrs in 1 atmosphere. The original volume, V1, it was 20.5 liters. The new pressure is 9.8 atmosphere, and I'm trying to solve for the new volume, V2. When I rearrange and plug in the math, I get that the new volume is 2 liters. And that's exactly what I expect. I increased pressure, and if you go back and read the problem, I increased the pressure by a factor of 10. Boyles Law tells us if we increase pressure, we expect to decrease, volume. That should say volume. Okay? The second law we're going to talk about today is Charles' Law. And whereas Boyles Law related volume and pressure, Charles' Law relates volume and temperature. It turns out that volume and temperature are directly proportional, just the opposite of Boyles Law. So as temperature goes up of a gas, its volume will also go up. It makes sense, right? If you heat a gas up, you expect it to expand. So you do expect volume to go up. So this is the mathematical equation of Charles' Law. If you are to graph Charles' Law, because they are directly proportional, there's no downward curving line, it is a linear relationship. Now each gas has its own precise linear relationship, but what's very interesting is when scientists were studying all the different gases, they realized that the intersection of volume and temperature for all gases was the same. So if you look at the intersection, it would be when is the volume of a gas equal to 0? Now that's impossible, but theoretically what scientists did is they extrapolated these linear relationships they were getting until the volume was 0. And it turns out that all gases, when they're presumed to have 0 volume, it occurred at an unusual temperature, and that temperature in Celsius was minus 273 degrees Celsius. That's where the concept of Kelvin came. So scientists called that absolute 0 and developed a new temperature scale called Kelvin, and the point at which all gases reached 0 volume was defined as absolute 0 or 0 Kelvin. Charles' Law, practical application. This is actually a kind of a fun demo to do. But if you were to blow up a balloon, put it in ice water, and it shrinks. And that's because of Charles' Law. So remember, Charles' Law said that, that volume and temperature are directly related. So equal sum constant. So as volume, so let's do it this way. As temperature goes down, volume would also have to go down in order to remain constant. This ratio always remains constant. On the other hand, if you put a balloon in boiling water with a higher temperature, the balloon will expand, again demonstrating Charles' Law. Oh, hot air balloon, my very favorite. I actually used to, for a while, worked on my pilot's license to be a hot air balloon pilot. So, but anyway, that works on the same principle. It creates a big plume of fire to heat up the gas inside of the hot air balloon, and the balloon expands, and that carries it up into the atmosphere. So it's pretty cool. Oh yeah, this is even more cool. If you ever get dry ice or liquid nitrogen and you put a balloon in it, the balloon just turns into a crinkly mass. So that's a real fun one to do too. All right, so here's an example of a calculation using Charles' Law. When you get these sample problems, you're not going to be told, use Charles' Law, use Boyles' Law. You're going to have to figure out which law is appropriate. So you're going to have to get in the habit of reading them carefully. So I would start kind of circling what the variables are. So in this one, it's talking about volume. And anytime it says a variable is held constant, you can ignore it. So that's just extra words. So let's just get that out of there. It's talking about volume, and it's talking about temperature. So what law do you know that relates temperature and volume? Well, that would be Charles' Law. And all of these laws are written in such a way that allow you to calculate a new volume, new temperature from original volume and temperatures. So try to work it out on your own if you want, or go to the next page and see me work it out. Oh boy, I really darked out. Let me rewrite Charles' Law. Alrighty, so the original volume was 247 milliliters. Temperature, remember, for gas laws always has to be in Kelvin, so I had to convert that. And we're trying to solve for the new volume and the new temperature in Kelvin. And when we rearrange and solve for V2, we see that the new volume is 311 milliliters. Always ask yourself with these if that fits with common sense. What did we do? We took our original volume, which was less, and we heated it up. What do you expect to happen to the volume when you heat it up? You expect the volume to go up, and it did in fact, so that's good. All right, another law is called Avogadro's Law. It's kind of got a lot of words here, so I'm going to try to underline the important parts. The bottom line is equal volumes of gases contain the same number of particles. Okay? Doesn't matter what the gas is. If you have a certain volume, so if I have 1 liter of a gas, it will always have the same number of particles as any other 1 liter of gas. So that's kind of cool. Okay? That's assuming you aren't messing with the temperatures like, with the variables like temperature and pressure and stuff. So, for example, you're going to start getting more and more familiar with the constant 22.4 liters. That particular volume of any gas contains exactly 1 mole of particles. So that can be used as a conversion factor. It's 22.4 liters is 1 mole of any gas. This relationship is not true with liquids and solids. Okay, equal volumes of liquids and solids contain vastly different number of particles, and that's because the packing density of liquids and solids varies a lot. Gas particles are always far apart because they don't have those intermolecular attractions. If you were to plot Avogadro's law, just like any direct correlation or direct relationship, you're going to see a linear relationship. Okay, so straight line here. And basically that's showing you that as the moles of a gas increase, the volume also increases. One final, there are kind of 3 laws that we think of as going together. And that would be Boyles Law, Charles' Law, and the Guy-Lussac Law, this one. Okay, those are all the laws that relate pressure, temperature, and volume to one another. So the Guy-Lussac Law relates pressure and temperature pressure and temperature are directly related, just kind of like we saw with Boyles Law. And so that means that as temperature goes up, we would expect pressure to go up. So that makes sense, right? Remember what happens to the molecules of a gas when you increase temperature? They start moving around and colliding more. So you would expect the pressure to go up. So that makes total sense. So here's an example of Gay-Lussac law. Let's imagine you have a deodorant can. And so it's a spray deodorant can. I know nobody uses those anymore, like an aerosol can. So it's a metal can that's rigid. It has a set volume, okay, constant volume, because it's metal. You know you're not going to change the volume. So you can kind of ignore. Remember I said if something's held constant, you can ignore it. So they're giving you an original pressure and an original temperature. And they're saying what would happen if you put that aerosol can in, let's say, boiling water. So we're talking about pressure and temperature. That is Gay-Lussac's law. So half the difficulty is deciding what formula you want to use to solve the problem. The actual solving the problem is not tough at all. Okay, so I really should have, I just told you that volume was kept constant, and so I am going to, I'll explain what I did in a bit, but for now I'm going to get rid of the volume terms because we know it's a rigid container, volume is constant, and so we're just going to look at the Gay-Lussac part of this law. Volume is constant, so again I'm going to ignore the volume term. And temperature has to be in Kelvin, so we converted them all to Celsius by adding 273. And that tells us that if you have a container of any type of aerosol that's normally at 1 atmosphere, no extra pressure, and you heat it up, let's say even in boiling water, pressure inside that can goes to almost 5 atmosphere, which is really high. So this explains why it's so dangerous to take any aerosol can and throw it in a fire, which some ignorant people have done before, because it will blow up like a bomb and be extremely dangerous. And that's because the pressure inside that can is going up extremely high. So I will, in just a moment, talk about why I even had the volume in here when it was constant. Alright, so I have had several students that really find it difficult to keep straight which is Boyles Law, which is Charles, which is Gay-Lussac's, how do they look, what do we do? There's something called the combined gas law. So if you look down here at the bottom of the slide, that has all three variables, pressure, volume, temperature. And if you only remember one law, it is the combined gas law, because I'm going to show you how to use this wonderful law to derive Boyles, Charles, and Gay-Lussac. So let's say, for example, the problem that we just worked, the volume is constant, doesn't change. That would mean that you would get rid of the volume term because it's held constant. And then what are you left with? You are then left with Gay-Lussac's law. Let's imagine now that instead of volume being held constant, that pressure is being held constant. Let's say whatever we're doing is open to atmospheric pressure, and it doesn't change. And so we're going to get rid of the pressure term. And what do we have left now? Whose law is that? That is Charles' law, volume over temperature. And finally, let's say that we hold temperature constant. Temperature doesn't change. So we're going to cross out the temperature term in the combined gas law. Whose law are we left with now? Boyles' law. And so again, if you just memorize the combined gas law, you can use it for any of the other gas laws. Alright, so we're close to being done, guys, about 3/4 of the way done. Probably the most important gas law of all is called the ideal gas law. And you don't really need to know this, but this is a nice summary of Boyles, Charles, and Avogadro's as far as proportionality. Volume is inversely proportional to pressure. Volume is directly proportional to temperature. It's Avogadro's law also tells us volume is directly proportional to number of moles. So do make sure you understand these relationships. If we combine all these, though, in a proportionality, we get something that looks like this, and that led to the development of the ideal gas law. The next two pages are out of order, so I'm going to flip 2 slides from now. All right, so going back to this slide, the different values for R, okay, and again you can see it just depends on the units you're using. The more common unit that we'll use for gas laws is liters, atmosphere, moles over Kelvin, and it's 0.08206, okay? And onward. So the relationship that I just showed you, proportionality, scientists put in what we call a proportionality constant, which is called the universal gas constant. And the value of R, the universal gas constant, that makes all of these proportions work is R. So there are a table of R values or gas constant values, and you will select the one you use based on the units of all the other variables in the equation. So now I'm going to go back to the last slide. All right, so here we go. Let's talk some more about the ideal gas law. PV equals nRT. That gas law describes what scientists call ideal behavior. And most gases, under most circumstances, behave ideally, and it's okay to use this equation. We'll talk about the exceptions. But in general, a gas is most ideal if it's under low pressure and if it's under a higher temperature. Okay? Low pressures and higher temperatures are things that make gas molecules far apart, and that gives them what we call their ideal behavior. When do you use an ideal gas law, and when do you use the combined gas law or some rendition of it? Well, it depends. If you have the properties of a gas right now only under one set of conditions, you will use the ideal gas law. Okay? It only has one set of conditions. If you're reading a problem that's telling you you're changing one or more variable, you're changing the pressure or you're changing the volume, that's when you want to use the ideal gas law. Here's an example that would use the ideal gas law. They have given you volume. They have given you number of moles. The number of moles right there should tell you it's ideal gas, because number of moles does not show up in the combined gas law. They give you pressure, and they ask for temperature. That's just a setup using the ideal gas law. PV equals nRT. You've got to have your table of R values on hand to work these problems. I will give you R values on any quiz or test, but while you're working your problems, you're going to want to have that handy. You can try to work this problem out on your own, or you can go to the next page with me. All right, all you have to do is plug and chug. Okay, pressure they gave you, 1.85 atmosphere. Volume, 47.3 liters. Moles, 1.62 moles. Here's the R value that has units that match all the units that were given to us in the problem. And we're solving for T. Rearrange this equation and solve for T. Remember that temperature will always be in Kelvin. Be careful, because some problems may try to trick you and ask you for the answer in Celsius. If that's the case, you need to subtract 273 from the Kelvin value. So if it asks for Celsius, the answer would be 385 degrees Celsius. All right, only a couple more quick concepts. Molar volume. That, by definition, is the volume of 1 mole of gas. Okay, molar volume. This is where we get our 22.4 liter value that you may have seen before and that I mentioned at the beginning of this lecture. If you take the ideal gas law and you rearrange it so that volume is on one side by itself, and you plug in all of the standard conditions that we've learned for gases. And so that would be 1 mole. Our value doesn't change. Standard conditions for a gas are 0 degrees Celsius, which is 273 Kelvin. Standard pressure is 1 atmosphere. When you plug all those values in, you get that the volume of a gas under standard conditions is 22.4 liters. And we say that 22.4 liters is the molar volume of any gas under standard conditions. STP means standard temperature and pressure. So what that means in real life is that if you have a set volume of any gas, doesn't matter what the gas is, and in this case we're setting the volume at 22.4 liters, you will have the same number of particles of gas inside that volume, regardless of the identity of the gas. Okay? And it so turns out that in 22.4 liters, you will have exactly 1 mole of whatever gas you have. That's a really important concept to have grasped. All right, and the final concept, density. You know density to typically have units of grams per milliliters. Doesn't have to be. It could be grams per milliliter, but it's usually that. In any case, it's a ratio of mass of a substance to the volume it's taking up. The mass of 1 mole of anything is called molar mass, just like the volume of 1 mole of anything is molar volume. Okay? How do you get density? This is a formula you will have to memorize. Density is molar mass divided by molar volume. So check this out. Molar mass has units of grams per mole. Molar volume has for a gas has units of liters per mole. So when you simplify this, let's see, moles cancel out, and you would get density units of grams per liter. So again, remember, write it down on a note card or something, that if you're asked to calculate the density of a gas, you take its molar mass and divide it by its molar volume. So here's an example. Here's the density of helium gas and the density of nitrogen gas. Helium has a molar mass of 4 grams per mole. Just get that from the periodic table. If we're under standard conditions, which this problem told us we are, the molar volume of any gas is 22.4 liters, and therefore the density of helium gas is 0.179 grams per liter. All right? So, and here's the density of nitrogen, calculated a similar way. Notice nitrogen is one of the diatomic gases. That's why its molar mass is 28 and not 14. All right, so using the density of gases and the molar mass, there's a couple other forms of the equation that you need to be familiar with. This is going to ultimately lead you to an equation that allows you to calculate the molar mass for a gas, and you won't need to do the derivation, but I just don't want to pop it out of nowhere for you. So if you rearrange the ideal gas equation, you can get it in this form, which is moles over volume. Moles over volume sounds kind of like density, doesn't it? The amount of something in a certain volume. And so starting with that, if we were to make some substitutions, if I were to ask you, how do you relate mass and moles of a substance? You would, I hope, tell me that moles equals the mass of the substance divided by its molar mass. And so if I just substitute this relationship into this formula for N, so wherever there's moles, I'm going to say mass over molar mass. Remember, that equals moles. Okay? I still have to keep the rest of my equation, the V, and pressure and temperature. Okay, and so now if I rearrange this equation so that I have mass over volume on one side and everything else on the other side, that's how I got the equation for density. That's another way to solve density. But I want you to pay attention to this, because in a minute you're going to have to solve for molar mass of a gas. All right, so I rewrote the equation just as it was written on the last page. Okay, kind of another form of the ideal gas law. This is density. If we rearrange it, like if you had a problem that asked you to solve for molar mass, this is what you would get. This is how I remember this equation. I've told you my memory isn't so hot. So what I remember is that mangy mutts, MM, put dirt, okay, kind of ignore the R, over their P, okay? Mangy mutts put dirt over their P. That's how I remember that formula. Here's an example. All right, so let's say you're on the test and you're reading this question, and if you're like most students, you're like, oh my gosh, I have 25 gas laws I have to remember. I don't even know what's what. Here they're giving you pressure, they're giving you volume, they're giving you temperature. So you might start writing the ideal gas law, but you see density. Whoa, and there's molar mass. Another name for molar mass is molecular weight. Anytime you see density or molar mass, you need to write that cute little formula I told you how to remember. So before I do anything, I'm going to say, okay, mangy mutts put dirt over their P. That's it. That's all you have to do to solve this problem. Now plug everything in. And there we go. They gave you the density. Here's our value. Make sure you convert temperature to Kelvin. And here's pressure. So if you plug all that into your calculator, you get that molar mass is 33.5 units for molar mass, or grams per mole. And that is it. Make sure that you don't lose your common sense in these problems. If you get a molar mass that's like 0.5, that's impossible, okay? So remember molar masses on the periodic table, and the smallest atom, hydrogen, has a molar mass of 1. So you need to get molar masses that are within reason. Sometimes you can even kind of try to figure out what the gas is from its molar mass, but I really don't know in this one. That's it for this portion of gases, and there'll be another lecture coming up going over diffusion, effusion, and a few other facets of gases.